So, let us continue our example solving session. So, we will now solve example 3, and here it is related to interstitials. So, you are given that assuming equilibrium interstitial concentration, defect concentration of carbon in Fe. So, we are talking about steel, and given that delta SF by Kb is equal to 2 and delta HF is equal to 1 electron volt per atom, what you need to find is at 600 degrees Celsius, find equilibrium concentration ratio of interstitial. That is, you have to find Ni by Ni, and second you have to find weight percent of carbon in Fe. So, basically you are finding same thing, but putting it in a different terms. Okay, so again we start with what we know. Xi equilibrium can be given as and it is given that HF is 1. So, it is minus 1 and it is in per atom. So, again we will use Kb, we will just use 6.2, you can use 617, it is not a big deal, you will end up with very close value. So, this comes out to, once you solve it, you know delta S by R, which is 2, and when you solve this you would see that this is okay, there is one correction here, this is supposed to be 1 not 2. So, I had the earlier written delta SF by Kb equal to 2, but that is that was a mistake, it should be taken as delta SF by Kb equal to 1, otherwise you will not get the final answer same as mine. Now, X equilibrium, when we write X equilibrium, we are actually writing X equilibrium in terms of total number of lattice sites, and therefore, this is 4.65 into 10 to the power minus 6. But what we need is Ni by Ni. So, what we need to find here is what is the number of interstitial sites. For that, what we need is to understand how many Ni are there with respect to N. So, what is Ni as N equal to? So, let us see what are the information we have. It is iron, it is at 600 degrees Celsius, and we are talking about carbon. So, at 600 degrees Celsius, carbon is in BCC form, Fe is in BCC form, and carbon in this sits in octahedral. That is something that we showed you in the earlier lecture. So, now that carbon sits in the octahedral sites, then it would mean that Ni is equal to 3N, and therefore, over here if you want you will have to divide it by 3. So, this solves our first part. This is the equilibrium concentration ratio of interstitial in these terms Ni by Ni. So, you see that here we need to know how many interstitial sites are there with respect to the lattice sites, and that information is given because we know it is iron. So, it is BCC at 600 degree Celsius, and we are talking about carbon. Carbon sits in the octahedral site. So, you remember that when we derived, we said that Ni will have to be will depend upon what is the structure and which particular interstitial site we are talking about. So, this is the information. This is now you see how to use this information. Next, what we need is to solve weight percent of carbon in Fe. Now, we see that this is a very small quantity Ni by N. Therefore, it means that the number of the total number of in the denominator, the total number we can take as 1, and there 1 meaning for each one atom there are so many carbon atoms, and there is so for each one atom of total units there is so many of carbon atoms and one Fe atom, and therefore, we will multiply it with 12 and 1 with 56 because that is the weight of iron, and therefore, this relation will look like this. So, this is the number of carbon atoms with its weight, and if we had added iron then we will get the total weight, but what we need is the weight percent of carbon. So, on the denominator we will divide it by 1 into 56. So, this is the total number of atoms, and we will assume that this is 1 atom of iron. So, it is 56 plus now, as you can see this is a very small quantity. So, with respect to this, so we can neglect this, and what we will calculate is this, and we need percentage. So, we will multiply it with 100, and what you get point 0.0001 weight percent carbon in Fe at 600 degrees Celsius. So, this is the equilibrium interstitial concentration that will exist, and these numbers are not the exact values, the numbers that you have been given delta SF by Kb and delta HF, but they give us very close to what is the real concentration value. We know that in Fe the concentration of Fe is very at 600 degrees Celsius in the ferrite form, the concentration of carbon in Fe is very small, and which is also what we get over here. If you remember, the solubility limit itself is in the BCC form is approximately equal to 0.008 weight percent, and that is at close to 700 degrees Celsius. So, this is itself a very small quantity, and at lower temperature the equilibrium concentration, we are not talking about doping or not talking about alloying, it has to be much smaller. So, these values are plausible. I would not say realistic, but plausible. So, now we have solved 3 examples in different kinds or different types of problems to understand defect concentration. Now, what we will do is we will move on to one important property or phenomena exhibited because of point defects. And what is that? It is diffusion. So, most of you would know that what is diffusion. diffusion is movement of atoms along or against, actually against meaning in the negative direction of concentration gradient. But this is not really the fundamental definition. Let me tell you why. Let us take two different systems. In the first system, we have here is a B rich system, B rich material, and here is the A rich material. This is one material, this is two material. Now, here because we have the system is such, let us say that B atoms are moving from here to over here and A atoms are moving from over here to here. So, you would say okay, yes, this is not the big deal, this is what we are expected, but that is not really true. You may also get a situation like this where you still have it need not be the same. When I say B rich, I do not mean that this is the same element, this is the same element. We are talking about two systems, and it is possible that in this system whatever the interaction are such that A goes from over 1 to 2 and B goes from B to 2, from 2 to B goes from 2 to 1. So, this is something that you are not very familiar with probably, and you would think that this is not really diffusion. This is what is called as uphill diffusion. This is more common. This is less common. This is along concentration gradient. This is against concentration gradient. So, what is the fundamental? So, now if I now tell you that this is something really happens and this is also diffusion, then what is the more fundamental principle behind it? Let us look at it. So, if we draw the free energy diagram for the two systems, this will look more or less like this. So, this is A, pure A, this is pure B, and in this particular system we have free energy something like this, and most likely your system 2, which is A rich, is somewhere over here, system 1 which is B rich is somewhere over here. Now, if you take the slope which will give you the chemical potential at these concentration, so this will give you chemical potential of B in system 2, this will give you chemical potential of A in system 2. Similarly, let us look at the concentration gradient for the chemical potential in for A and B in system 1. So, for this we will have in the system 1 A will have chemical potential mu A1, in this will have 1. Now, here what you see is that mu A2 is greater than mu A1, and that would mean that A must flow, because this is a higher chemical potential. So, we know that to get to lower energy, the system must attain or try to achieve lower chemical potential, and therefore, the elements the A component will diffuse from 2 to 1. Over here what we see is that mu B1 is greater than mu B2. So, for the same reasoning B moves from 1 to 2. So, this also happens to be along the concentration gradient. Now, let us look at the other case. Since I do not have space, let me go to the next page, and here let me draw for the second system, and I will have to replot this one. Quickly let me draw this. So, this is 1, this is 2, this is B rich and this is A rich, and we have said that B moves from 2 to 1, A moves from 1 to 2, that is against concentration gradient. So, over here how is actually the free energy plot look? How does the free energy plot look like? It probably looks something schematically something like this, and here most likely your system 2, which is, so so this is A, pure A, this is pure B. So, system 1 which is B rich is somewhere over here, system 2 which is A rich is somewhere over here. Now, here also let us try to get the chemical potential of the two components. Now, here, so this is for system 1, and here we will have mu A 2. So, in system 2 the chemical potential for A is this, and in system 1 chemical potential for A is this. Over here chemical potential of B in 1 is this, and chemical potential of B in 2 is this. So, now what do we see here? We see that mu A1 is greater than mu A2, and now like I said that this, if this is the higher and this is lower, so A must diffuse from 1 to 2. This is what is happening. For B, mu B2 is greater than mu B1, therefore, B must diffuse from 2 to 1. So, now we see that indeed what is predicted by chemical potential is what is happening over here. It means that in both the cases movement or diffusion takes place along chemical potential gradient. So, here also so this is the more fundamental principle, is what I am trying to come to the conclusion. So, the diffusion takes place along chemical potential gradient. So, now let us look at this diffusion in a more detailed manner. So, let us first look at what is called as interstitial diffusion, and I would refer you to the book by Porter and Stirling, because it explains this concept in a very lucid manner. Okay, so, we are talking about interstitial diffusion, meaning inside the matrix, inside the material that we are talking about, there are some interstitial defects or interstitial impurity which diffuse. So, we are talking about how they diffuse. So, we let us draw it, let us draw this schematically. So, let us say these are the lattice atoms. And let us say these are our interstitials. So, it is not everywhere, they are at some places. And what I am trying to show here are that there are two planes that we are talking about. This is plane 1, this is plane 2, and the way we are showing is that concentration is higher on this side and lower on this side. So, this has N1 atoms per meter square and this has N2 atoms per meter square. Now, diffusion, why does the diffusion take place? What is the fundamental theory behind it? It is called the random walk theory. So, the atoms, or in this case the interstitials, they are moving randomly in some direction because of the inherent vibration. They move, keep hopping from one side to another side, and in the process they see lower energy to the side where the concentration is lower, or in fact where the chemical potential is lower. For now, we will assume that the chemical potential gradient is along the same direction as the concentration gradient. And now, let us consider these two atoms to derive the relation for that. Consider these two planes, and let us say that tau b is the quantity which talks about average atom jumps per second, but this is in random direction. But this random direction is not in 4 pi direction, meaning in the solid 4 pi direction. These atoms have some coordination number, and in the configuration given here we can assume that this coordination number is equal to 6. Therefore, if we are talking about movement along only one particular direction, what we are looking at is 1 by 6th. We are looking at 1 by 6th of this atomic jump. So, now the flux of atoms that is moving from 1 to 2 can be given as, so this is flux of atoms from 1 to 2, this will be equal to 1 by 6 tau b, number of atomic jumps, into the density of atoms that is present there. So, this will be equal to N1, and the units would be atoms per meter square per second. Similarly, there will be flux of atoms from 2 to 1, and this will be similar, except density on the other side will be different, which is N2, and therefore, we will, as you can see, this is a lower quantity, this is a higher quantity. So, less number of atoms are going from 2 to 1 and more number of atoms are going from 1 to 2, and therefore, there will be a net movement of atoms from 1 to 2, which can be represented as Jb equal to Jb 1 to 2 minus Jb 2 to 1, which is equal to 1 by 6. Now, if we assume that the separation between the planes is equal to alpha, then it can be easily shown that Cb1, that is concentration of atoms at 1 is equal to n by 1 alpha. This will be in per meter cube, and Cb2, concentration of atom at this line 2, at this plane 2 is equal to n2 by alpha, and therefore, we can convert it to but this change in concentration from 1 to 2 can also be written as minus alpha, because concentration is changing, is decreasing when we go from 1 to 2. So, Cb1 minus Cb2 is decrease, which is represented by minus sign, del Cb by del alpha, sorry, del x, that is assuming this is the x direction. So, we can again replace it over here, and what we get is a quantity like this. Now, at this point you would start to see that this looks like a familiar equation. So, what is this equation? Jb equal to minus 1 by 6 tau b alpha square del Cb by del x, and if you replace this by the quantity called as dB, then now you would be completely convinced that this is a equation that you already know, which is also called as Fick's first law of diffusion. So, the phenomena that is represented by this vacancy, which is the diffusion, can be represented by this equation, which is flux of atoms, flux of displacement of atoms can be in this particular case we are talking about one direction. So, this flux of atoms can be given by Jb equal to minus dB del Cb by del x. So, this is a very useful relation, and we will look at more, and you can also add complexity, that is you can talk about 3 dimensions and all the 3 dimensions. So, this relation, this equation would become a little bit more general, but now you understand how do we derive this equation based on the interstitial impurity. So, we will come back to this and we will talk more about diffusion in the next class, which is an important phenomena related to point defects. So, see you next time.